In this session, we will cover the components of the Bayesian Evolutionary Analysis Sampling Trees, or BEAST package. BEAST is a Bayesian MCMC analysis software which focuses on rooted trees with timescale. As we've covered in the previous sessions, numerous models are included and can be used in a multitude of combinations. BEAST includes a suite of tools for setting up standard analysis and to help diagnose and summarize the outputs. Beauty is BEAST's user interface that allows the selection of a range of commonly used models, including integration of age of samples, selection of strict, local, and relaxed clocks, selection of nucleotide substitution models, manipulation of priors, operators, and MCMC chain settings, and finally creating XML files as shown on the right. BEAST reads the instructions from the XML file and performs the analysis. In the end, it produces at least two files, a log and a trees files. Tracer is a tool that allows the visualization of the MCMC mixing, inspection of convergence of the parameter, and summarizes the files. Particularly, it allows us to inspect the distribution of the results for parameters, provides estimates for means, median, and of the Bayesian equivalent of a confidence interval, the 95% highest posterior density, or HPD interval. This is the smallest interval that contains 95% of the posterior probability. Tracer is also an MCMC diagnostics tool. An acceptable chain should look like white noise or a hairy caterpillar, since that represents that the MCMC appropriately explored the posterior probability landscape without getting stuck in local maximums. The effective sample size, or ESS, is the number of independent draws from the posterior distribution that the MCMC chain is equivalent to. The ESSs are calculated as the number of samples divided by the autocorrelation time, or ACT. Now let's evaluate different chain behaviors. In this case, the chain looks like white noise, which is an indication that it is mixing well and sampling efficiently from high-density areas of the posterior distribution. This means that we obtained a good approximation of the posterior distribution in finite time. But this is not always the case. Sometimes the chain does not mix well since the samples are not being drawn uniformly from all over the stationary distribution. This is what we call a sticky chain. The way to go about it is to identify the parameters where the chain gets stuck and tune the operators to make better proposals. If the chain looks like this, where we have parameters converging to two different values, we might question if we are still in the burn-in phase. In this case, we would need to run the chain for longer and wait for it to converge to the stationary distribution. If it looks like a part of the chain is sampled from the stationary distribution, but the other part is not, it might mean that we are still in the burn-in phase, and thus we need to run it for longer. The way to confirm this is by running multiple independent chains and inspect if they follow a similar behavior. Also, this allows combining the results of identical chains to obtain better ESSs for regions that are not as well sampled in a particular chain. Sometimes, independently of what we do, the results might not converge to a particular value that could be represented by a normal distribution. In some cases, the model supports a bimodal posterior distribution, meaning that there are two or more possible estimates for our parameters, either not very well supported. This is usually not the desired answer, but might represent the truth. In this case, we could try fitting different models to our data and compare if different models explain the data better by using the algorithms available in BEAST. Tracer also allows combining log files. Another of BEAST tools is Log Combiner, which allows combining multiple logs or trees from multiple identical runs. Tree Annotator is a tool to summarize trees files or a combined trees file out of Log Combiner into a summary maximum clade credibility tree. Now, instead of working with a distribution of 10,000 trees or more, we have a single summary tree with posterior probabilities on the nodes that can be visualized in fig tree. Now that we went through the models and components of Bayesian analysis, while understanding that each analysis is unique, let me go over some general guidelines on BEAST best practices. Before you begin, know your data and plan your analysis carefully, reading the literature on how others have analyzed similar pathogens or to get information that could inform your priors. Before executing the analysis, you can also just sample from the prior, meaning running without data, so you can see the tendencies of the run and how it is influenced when you add the data. Always run multiple independent chains to look for consistency in the parameter values to which the chain converges to. After the analysis, combine chains and assess convergence and mixing. When checking your results, make sure to inspect the traces for strange behavior as discussed previously, particularly the posterior or joint chain. Also, investigate the time to burn in, as it is an indicator of how long you will need to run the chain. Make sure to exclude the burn-in phase before interpreting the results. Again, perform multiple runs of BEAST and compare the results. If the runs are sampling well and have achieved convergence, you can combine the samples from the multiple runs. Try to get all the ESSs above at least 100, but preferably higher than 200. To achieve this, sometimes we need to run the chains for longer and/or combine multiple runs. Some of the most common pitfalls of phylogenetic analysis are not using enough background data. For instance, in the tree on the right, the researcher inferred that human malaria was closely related to that of chimpanzees. But they should have been more careful interpreting the long red branch that connects the two clades. In a later study, after obtaining sequences from 3,000 plus apes in Central Africa, the authors found that human Plasmodium falciparum is actually more related to the gorilla lineage. We also covered the importance of removing recombinants, as these can severely bias the tree topology and parameter estimates. Additionally, always use simpler, less complex methods such as neighbor joining or maximum likelihood to build trees and have an overall understanding of the evolutionary patterns of your data before doing more complex and time-consuming analysis with BEAST. Next, always question odd results and review the models and priors used in the inferences, your alignments, and what has been already described in the literature. Finally, always be cautious of overinterpretation, particularly in sections of the tree where gaps may exist. So, the main take-home messages from these phylodynamic sessions are that inferring phylogenies allows reconstruction of the pathogen's ancestral relationships and recovery of hidden information, and that we can also use the phylogenies to identify recombination and natural selection. However, building a tree is only half the challenge, and the most important is to interpret the tree on when or where did the pathogen originate, or how is it evolving or spreading spatially. Also, keep on the lookout for new extensions of the models presented by the BEAST team and other phylogeneticists that are constantly working on new tools for more sophisticated and in-depth interpretation of the phylogenetic patterns.